Um, okay, so moving on. So that's one way for us to estimate the parameters of interest, right? So to recall, we have learned about the maximum likelihood estimator, where in this mode of estimation, we estimate the theta hat estimates um, theta by maximizing L, which is the likelihood function. So in more technical terms, we can say that uh, we can write theta hat as theta hat equals arc max yeah, theta in number of omega, which is the Planck space. And what this notation here means is that argmax simply means take the argument that maximizes, and L theta is the likelihood function with respect to theta. Since the likelihood function, the sample is assumed to be fixed, and we only allow the theta, the value of the theta, to vary. Okay. So what this notation simply means is from theta, from any value of theta, um, from any value in the parameter space, right? Take the value of theta within, which is a member of the parameter space, that maximizes the argument of the likelihood function, which is theta, right? So take theta that maximizes the likelihood function, which is function of theta. Okay, so that is all in all what MLEs are about. So now I think we can move to proceed with discussing another important definition. Okay, all right. Um, wait, yeah. All right. So let's say you have let's say you have a sample, right? And this sample follows some distribution uh, with mean, let's say, mu and variance sigma squared. Now, um, okay, good. Sorry. Let's say, let's say we just use the past example where the sample follows the normal distribution with mean mu and variance sigma squared. Okay. Let's say we just know that we don't know what the quantities of the variances are. We just know that it follows normal with the variance here, the mean here, mu, and the variance sigma squared. Okay. So as we know earlier, the mean is let's say if we want to find the sample mean, that would be x bar 1 over n, and then this is the sum of xi, right? I from 1 to n. And then if you want to find the sample variance, here denoted as square, we have here this formula, right? 1 over n I equals 1 into n, and then xi minus x bar. Now, why use the sample mean instead of the population mean? Because the population mean is because we're simply estimating the variance from a sample, right? So in a way that we cannot, mm, we wouldn't know lah what is the true value of, let's say, mu here. Okay, so if we're estimating everything from scratch, this is how we find the variance, right? Okay, now if you try to take the expectation of both of these variants, right? We will have okay, let's say the expectation of x bar is just expectation, and then you expand that expression, right? And then since the expectation is let's say it's a linear operator, lah, still remembers the linear algebra that you learned, right? So it follows the property of the linear operators. That is, this becomes true. Okay? And since this, since we suppose that this is true, right? And then, oh, I forgot to add. The condition here is that the sample is identically and independently distributed. So what that means is every xi here is independent and identically distributed as normal distribution. So hence, the expectation of every random variable in the sample xi will equal to mu, right? Okay, and this is simply 1 over n and mu. Okay, so now we see that um, the expectation of x bar here, which is a sample mu, corresponds to the true value, right? Corresponds to the true value. That is the true value of the mu. So we have an expectation that, in a way, uh, this expectation may be provided that the sample is large enough, will approach the true value. And this property, the property of um, estimating the correct actual value here, is what we call bias. And so since the expectation of x bar, now x bar is an estimator of theta. Sorry, estimator of mu hat. Sorry, mu. So we denote it as mu hat. And since if let's say the expectation of mu hat, what is the estimator of mu here equals mu itself, we say that x bar is unbiased. Okay. Okay. All right. So and then, but we see that it doesn't hold for the variance actually, to operate the variance punya estimator lah, right? Sebab as you can see here, if we try to find the estimator of s squared, what do we have? Okay, we have this. Okay. All right. Okay. This simply follows from the properties above lah. Okay, so if we were to expand, we will have uh, UXI X bar, UXI X bar plus X bar squared. Okay. All right. Yeah. And we can further expand this by saying uh, this one. Since the sum here, since this sum here, this is part of the sum, right? And only we can treat x bar as if it's a constant. Okay. And same goes with the last expression. Wait, I think the other sheet let's keep. Okay, that's correct. And we have 1/n expectation sum from 1 to n xi to uh, the x bar and x bar, right? Because the sum of all the n variables in the sample size n equals the sample mean multiplied by n, right? Plus n x bar squared. So now we know that these two multiply, so we have the same expression, except that this one is multiplied by 2. So we can just take this, simplify, and get this. Oh, sorry, about okay. Okay, so now you have this final expression here. Sorry, no, not final. Uh, yeah, we have this expression. Mm, okay, okay. So okay, this is quite a confusing. I know this can be somewhat confusing to work with. Okay, but let's approach it step by step. Okay, right. So if xi if the sample xi x1 to xn, I just write xi from now on, follows the normal distribution, then we know that expectation of xi squared is the second moment equals just the variance of x plus the square of x, right? And this is simply variance of sigma squared plus mu squared. True, right? Okay, what about x bar? X bar, since x bar is like uh this here, right? And so um and we know the expectation of x bar already, right? This is just mu. And so we can also find it using the same method that we use for the like UXI here, which is just this variance of xi, the variance of expectation of x bar squared equals the variance of x bar plus the square of x bar. Now, how do we find this, right? This you can find by simply expanding lah. So you know that variance of x bar here is variance of 1 over n sum xi, okay? And since we follow the same assumption, that is IID assumption here, we can simplify this. Remember for variance, we can bring the 1 over n outside, but it will become 1 over n squared. And then we take the sum, and then we take the variance of xi. And this is true, right? And since the variance of xi are similar from I equals 1 until n, we can say that this is just variance squared. And sorry, sigma squared. And since sigma squared here is constant, with this sum here, so summing from I equals 1 until n, this brings us to the final answer of sigma squared over n. So yeah, okay, right? Okay, so returning back to this equation here, okay, so now we have the value of variance of x bar. So we can find this thing, expectation, second moment of x bar, which is ex bar squared, by just taking the values that we obtained in here. Okay, and what that means is for this expression here, we can find our final value, which is the expectation. If I return back to the expectation of the sample variance earlier, which is 1 over n, 1 over n, sum 1 until n. Now, we know what ex I squared is, right? Which is sigma squared plus mu squared. And we minus n, and we also know what x bar, expectation of x bar squared is, which is this plus squared. So we just add them up. Okay. Now this is constant, so we can apply same simplify again, which is just 1 over n and 1 squared plus mu squared plus we multiply n here. Yes. Okay. Plus n plus Um, describe. Okay. Wait, yeah. Wait. Mm, wait. So this oh wait, there's silence mistake. There's mistake. Sorry. Okay, so here is just question. Mm, oh, sorry. There's a careless mistake here. My apologies. So we should have this. Okay. So here we can just 1 over n is n multiplied by the sum I plus 1 to n. And then we just take what is it? This expectation here. So like this. Okay, and then we minus dx square bar, dx bar squared. And this just this plus this. Okay, also you can say that the sum here cancels out because again this is a constant. Okay, and then you will have this sigma squared plus mu squared minus sigma squared over n minus mu squared. These two cancels out, and so you will have sigma squared minus sigma squared over n, or n minus 1 over n sigma squared. Uh, now we note that um this here, this function here, um it's not the same as theta, right? Okay, so hence what that means is that the estimator 1 over n I plus 1 n xi is minus x bar squared is biased. So what we can say is that MLEs, that is the maximum error estimators, are not always unbiased. Okay, so specifically for the formula for sample variance, right? What do we do about it? What do we do so that we can have an unbiased estimator for the variance? Okay, now if we note that um, since this is a normally distributed random variable, right? Xi is a normally distributed random variable. So recall that, let's say I have a random variable z squared, and this z squared here is the sum, is basically uh, the square of xi minus mu over variance, and then I square this, right? So z is equals to, let's say, similar to the formula for z score, right? You take the random variable, you minus its mean, you divide by the variance. So if you were to square this, then you know that this equals to uh, chi-square, chi-square random variable with degree of freedom 1. Okay, now if you were to do the same, with, if let's say we say we assume that sum of I equals 1 at the end, stack I squared, right? Equals to the sum of I equals 1 at the end, and then we insert back the original random variable z here. Okay, and so this will be chi-square with degree of freedom n. Okay, why degree of freedom n? Because you have n values that is allowed to vary. Yeah. Okay, so return back to our original assumption. Return back to our original sample variance formula. Okay. Um. Okay. So S is 1 over n. S is 1 over n, sorry, 1 over n, sum of I equals 1 at the n, xi minus x bar squared. Okay, now suppose that this function here, okay, no, how do I explain this? Okay, suppose that we multiply both sides by let's say variant. We divide both sides by sigma squared. So you have sigma squared over s squared over sigma squared equals 1 over n xi x bar. Correct? And so this here is similar to this, right? Except that the mean is estimated from the sample. So since you have n of these random variables, now for this part here, we say that this follows the we say that this follows the I square and the variable with degree of freedom n minus 1 instead of uh the n degrees of freedom. Why n minus 1? You can look it up online, but the way I understood it at least is basically the degree of freedom um, reduces for every time you need to estimate the quantity. For example, in order to estimate the sample variance, you need to estimate the sample mean, right? So you're estimating twice, not just once. Okay. So that is why when you estimate the first time, that is you estimate the sample mean, you reduce the degree of freedom by 1. And so when you actually have the sample variance, what you have is if you want to find the distribution of the sample variance, what you're going to have is the same chi-square random variable, only that it reduces by 1. Because as you can see, the mean here is not allowed to vary. It has to be fixed. But then you have n random variables, right? So not sure if you understand that, but yeah, that's the logic behind it. It doesn't come in straight foremost. Okay. All right. So uh if you have this, right, now that you have this random variable here, now that you have this random variable here, you can say that n s squared over sigma squared equals this. Sorry. Okay. Okay. And this is chi-square distributed too, right? Okay. So so this is chi-square distributed. So if you try to find the expectation, right, and at ns squared over sigma squared. So you have this. You take the expectation for both sides. Okay. Now, if you know that the expectation of for this part, yeah, we can simply say that we know the left part first. But yeah, let's just see on the right side here. Since this is chi-square, since this is chi-square with n minus 1 degrees of freedom, right? So what is it that what is the expectation of a chi-square random variable with n minus 1 degrees of freedom? If you recall from sets 1, that would be any expectation of a chi-square of random of degree of freedom r is r itself. So the mean is actually the degree of freedom. And since this expression here has degree of freedom n minus 1, so you will have this expression here, and that be this expression n minus 1. Um, and if you arrange back, since sigma squared and n here is constant, you will still have this you will still have this expectation here, n minus 1 minus n sigma squared. Okay, now this is just the same as the formula above, right? But we wanted to find the unbiased estimator of the unbiased estimator of the variance. So what can we do to make this, uh, let's say, return the true value, which is sigma squared? Now here we introduce an important concept. Simply put, what it what needs to be done is just introduce a form of correction on the original formula of the sample variance. And this is, I think, if I'm not mistaken, it's called the Basel correction. You can look it up. And it basically arrives at, looks at the formula, states the formula of the sample variance differently. That is, you state S squared and you take 1 over n minus 1. Sum of I is 1 over n, xi, x bar here. And then we square this. So if you multiply this, taking this formula here, S squared, you multiply it by n minus 1 and divide it by the variance, what will you get? You get this, right? This expression here. And this we know follows the chi-square distribution with n minus 1 degrees of freedom. Okay? And if you take the expectation of n minus square multiplied by s squared um, over sigma squared. Okay, okay. And so we know that this right hand side here is just n minus 1. And so that means if you were to rearrange s squared, that would be n minus 1 divided by n minus 1 multiplied by sigma squared. This is just the sigma squared. So now we have, with this correction, we now have the true unbiased estimator of sigma squared. And this help answers the question, why is the formula of sample variance has this n minus 1 here? Why? Because it's the requirement for it to be unbiased lah, as I have shown in this example. Okay, so we can say that because Basel correction, Basel correction, okay, makes it unbiased. All right. So that is, I think, all about the biasness of estimators. So I believe with that, that completes the first, I would say, part. That is like the definitional part of studying MLEs. And for the next video, we will proceed to studying the qualities, that is the quality and the further properties of the maximum likelihood estimator. Okay, thank you so much.